When a microscopic environmental antigen, like a pollen grain, first lands on a biological barrier, such as the lining of the respiratory tract, the tissue often shows zero reaction. The exposure is entirely silent. Yet, if that exact same pollen grain lands on that exact same tissue weeks later, the local cells rapidly engorge. Fluid leaks into the surrounding space, producing volatile swelling and redness within minutes. This stark contrast between a silent first contact and a volatile secondary response is the defining hallmark of IgE-mediated hypersensitivity. To understand how the body manufactures this reaction and how we can medically intervene, we have to map the precise 5-step temporal progression from that initial silent exposure to the final explosive clinical event. The difference between routine barrier defense and a lethal anaphylactic reaction is dictated entirely by a strict 2-phase biological timeline. The molecule at the center of this timeline is immunoglobulin E, or IgE, a highly specialized class of antibody. In healthy individuals, IgE operates as a frontline defender. It is localized almost exclusively at barrier sites, like the skin and mucosal membranes, where the body interfaces with the outside world. To produce IgE, the body requires a specific cellular environment known as a Th2-type immune response. A Th2 response typically evolves to fight off large extracellular parasites. However, in allergic disease, this specific immune response misfires. It identifies harmless environmental proteins as threats, making IgE the central mechanical driver of the resulting pathology. When a Th2 response misidentifies a harmless antigen, it weaponizes IgE. It turns the body's own barrier defenses into a primed trap, waiting for a trigger. This flowchart maps the 5 distinct stages of the allergic cascade, starting here with step 1, sensitization. Sensitization is the clinically silent first exposure to an allergen, beginning when an antigen-presenting cell captures the foreign protein. Once the antigen-presenting cell internalizes the allergen, it links directly with a Th2 cell, releasing signaling molecules to communicate the perceived threat. The Th2 cell responds by releasing specific cytokines, primarily interleukin-4 and interleukin-13. Cytokines are small proteins that immune cells use to communicate and coordinate behavior with surrounding cells. These 2 cytokines travel to a resting B cell and force it to undergo a genetic process called a class switch. The B cell physically alters its internal manufacturing mechanisms. Following this class switch, the B cell begins mass-producing Y-shaped IgE antibodies. Crucially, the outward-facing arms of these new IgE molecules are geometrically shaped to bind exclusively to the original allergen. Throughout this massive microscopic manufacturing process, the patient feels fine. There is no swelling, experiencing no itching, and absolutely zero clinical symptoms. Sensitization systemically manufactures thousands of highly specific biological tripwires, leaving the patient primed for a reaction, despite the initial lack of symptoms. Once manufactured, these newly minted IgE molecules migrate away from the B cell, traveling through the tissue towards resident immune cells. Their primary targets are mast cells and basophils, heavily concentrated along the body's barrier surfaces. Step 2 of our flowchart shows how they attach. The mast cell membrane is studded with empty cup-like receptors called Fc-epsilon-Ri. Fc-epsilon-Ri is a high-affinity receptor specialized to bind the tail end of IgE antibodies. The tail of the IgE molecule docks securely into this receptor. The bond is nearly permanent. The IgE points its antigen-binding arms outward, effectively arming the mast cell. The cell is now a sensitized, loaded weapon. It can sit quietly in the tissue for weeks, completely dormant, waiting for the allergen to return. The timeline now shifts to the re-exposure phase. Weeks or months later, the exact same allergen breaches the barrier site again. In step 3 of our diagram, we see the returning allergen approach the armed mast cell and interact directly with the outward-facing IgE molecules. Biology requires a strict mechanical failsafe here. A single binding event, one allergen attaching to one IgE antibody, will not activate the cell. Activation requires a mechanical trigger called cross-linking. The allergen must be large enough to act as a physical bridge, locking into two adjacent IgE molecules simultaneously and pulling their attached receptors physically closer together. This precise spatial clustering of the receptors on the cell surface is the definitive physiological switch. It initiates a glowing, cascading chemical signal straight down into the cell. This intracellular signal guarantees step 4, degranulation. Deep inside the activated cell, spherical vesicles, called granules, respond to the signal by furiously migrating toward the outer cell boundary. As they reach the perimeter, these vesicles fuse with the cell membrane, dumping a massive, highly concentrated chemical payload directly into the surrounding tissue. The speed of this reaction is absolute. Degranulation occurs within seconds of the initial cross-linking event on the surface. This microscopic chemical dump is the exact moment biological priming translates into a macroscopic clinical emergency. Allergic activation is an issue of spatial geometry. Mechanically clustering surface receptors is the exact switch that detonates the mast cell. The severity of the symptoms depends entirely on the chemicals inside that payload. We can categorize these chemicals into two distinct temporal groups based on when the mast cell creates them. The first category consists of preformed mediators. These chemicals were already manufactured and stored inside the vesicles, meaning they are released instantaneously upon degranulation. This split-screen matrix maps the chemicals. On the left side, we see the primary preformed mediators, histamine and tryptase. Histamine drives the immediate clinical symptoms. It rapidly binds to local tissue, causing the intense itching, the raised hives known as urticaria, and a rapid widening of the blood vessels called vasodilation. The second category consists of newly synthesized lipid mediators. As the right side of the matrix shows, the mast cell must manufacture these lipid mediators, leukotrienes and prostaglandins, from scratch upon activation. Because they are built on demand, their physiological effects peak later and last significantly longer. Leukotrienes directly cause sustained bronchoconstriction, a tightening of the airways, and prolonged vascular leak. These are the primary drivers of chronic asthma symptoms. An allergic reaction is a staggered chemical assault, dictated directly by the varying synthesis times of these specific chemical mediators. Mapping these mediators to their distinct temporal pathways reveals exactly how we can target them with pharmacology. Returning to our matrix, we see how an antihistamine works. It competitively blocks the cellular receptors for preformed histamine on the left pathway, quickly resolving immediate symptoms like hives. But antihistamines routinely fail to resolve the sustained breathing issues seen in severe allergic asthma. That failure occurs because the sustained bronchospasm is driven heavily by the right pathway, the newly synthesized leukotrienes. Antihistamines cannot chemically interact with leukotrienes or their receptors. To intercept this secondary lipid pathway, a clinician must prescribe targeted leukotriene modifiers. While localized symptoms like hives and asthma are highly manageable, the ultimate stakes of the IgE pathway escalate when the reaction goes systemic. If a massive dose of allergen enters the bloodstream, it cross-links IgE on mast cells throughout the entire body simultaneously. This systemic activation causes extreme, rapid vasodilation, resulting in a sudden drop in blood pressure and multi-system compromise, a condition known as anaphylaxis. Surviving anaphylaxis requires immediate medical intervention to reverse the vascular collapse. It proves that immunology is a science of biological timing and spatial geometry, where a silent microscopic connection can rapidly cascade into a systemic clinical event.